Hello everyone, we are from Group 3. Welcome to Hydraulic Factory 101. My name is Fatahillah Mahfud Ridho.
Hello everyone, my name is Geraldo Abarua. You can call me Gege.
Hello, my name is Welinda Griani Lawarana.
Hello, my name is Mutia Akhirina.
My name is Ahmad Farhan Solahuddin. You could address me Farhan.
My name is Rahman Laksamana Pratama.
So, what is hydraulic fracturing? Hydraulic fracturing, or sometimes just referred as a fracking, is one of well stimulation technique used to produce oil and gas hydrocarbon reserve that can be produced by a conventional means. This technique is done by pumping or injecting a highly rate and pressure fluid called fracturing fluid to the target formation in order to crack the formation.
Method of fracking has been around since 1962. The American Civil War era credited to Colonel Edward L. Robert. In this time, fracking is done with assorting explosive to the borehole, making a blast that crack the formation. In 1935, more than half a century since then, the idea of replacing explosive with a high pressure injection of a fluid, this name hydraulic, emerged, brought by an sponsor. In 1947, the first practical use of hydraulic fracturing is conducted at Hugoton Gas Field, Great Country, Kansas by Stanolin, with basis of study done by Floyd Faris of Stanolin Oil and Gas Corp. In 1948, the process is further explained by J. Beckler of Stanolin on his paper. In 1949, the first commercial use of hydraulic fracturing done by Halliburton in the separate field at Stephen County, Oklahoma and Archer County, Texas. Since then, hydraulic fracturing started to use widely, especially in US.
There are several reasons why hydraulic fracturing is preferred by many people in industry. The first reason is petroleum-based energy demand. The world demand for energy has increased exponentially in the past and is expected to continue increasing for the foreseeable future. This triggered primarily by population growth and higher standard of living around the world, especially in the developing world where the most of the population live. And also there are other energy that is non-fossil energy, but many people still prefer fossil fuel, especially in the developing country. To fulfill this increasing demand of the oil and gas, many methods of increasing production rate emerge, such as hydraulic fracturing. In the natural state, most of oil and gas do not produce at their optimum level, but hydraulic fracturing can address multiple challenges to efficient production, thus improve the production rate. Production rate performance will eventually decline to a level below which production is not economically advisable. Hydraulic fracturing increases the ultimate recovery factor that corresponds to the economic cutoff of production. The second reason is producing unconventional reserve. Reservoirs are classified into two types, namely conventional and unconventional reservoir. The conventional reservoir produce from the medium to high permeability formation that form naturally on the formation. But unconventional reservoir produce from very low, narrowly isolated to low permeability or tight formation, such as tight gas, tight oil, shale gas, shale oil, or CBM, etc. With hydraulic fracturing, it is possible to produce this kind of reservoir economically, increasing the production of oil and gas industry in the country.
As we explained earlier, hydraulic fracturing is done by injecting a highly rate and pressure fluid to torture the formation in a wellbore. This act will cause initiation and extension of hydraulic fracture, making change in the flow regime and permeability, thus increasing the production rates of well. But the pressure required for the fracture initiation depends on the values of: first, the three in situ principal stresses, mainly as vertical stresses, minimum horizontal stress, maximum horizontal stress. And the second one is formation mechanical properties, and the last is the formation tensile strength. Meanwhile, the pressure required for the fracture extension is dominantly controlled by the least in situ principal stress. The orientation fracture is perpendicular to the direction of the same principal stress. During the injection, the fluid pressure inside the fracture is higher than the least in situ principal stress, and this keeps the fracture open. But after the injection stops and the pressure is allowed to drop and the fracture will begin to close. In order to keep the fracture open and productive or permeable, after the treatment, a propane is mixed with the fluid and injected inside the fracture to keep it open during production operation.
After completing the well, fracturing job consists of several sequence procedures. This sequence can be varied in each well, where each of them have their own particular formation condition, but the process essentially same. This also include the specific blend of fracturing fluid used for each specific formation. The first step is pre-pad or acid stage, consisting of mixture of low to mid-strength acid and water. Serves to clear cement, debris in the wellbore, and provide an open conduit for other fracking fluid. By dissolving carbonate minerals and opening fracture near the wellbore. Second step, pad stage, consisting of a slick water, mixture of water and viscosifier or friction reducer, usually polymer, without propane material, serves to open the formation and helps to facilitate the flow and placement of propane material. Third, prop or slurry sequence stage, consists of a mixture of fracturing fluid and propane, intended to keep open or prop the fracture spread or enhanced during the fracturing operation after the pressure is reduced. Fourth, flushing stage, and consisting of a volume of fresh water sufficient to flush the excess propane from the wellbore.
To accomplish the task of fracturing the formation, the fluid used to create the fracture in the oil and gas and reservoir, which will effectively increase the area of the wellbore, must have a large number of unique attributes. This requires a true understanding of the complete rheological properties of the mixture of chemical compounds which make up the fracture fluid and its propans, that is designed to accomplish the task of creating a network of fracture extending away from the wellbore and is interlaced with the natural fracture system of the cell reservoir. Fracturing material consists of two main components, fluid and propan, where the fluid commonly is a mixture of water and additive. So, we can conclude that a fracturing fluid mainly composed by three materials: primary water mixed with propan, usually sand, and small amount of chemical additive. Although the excess percentage of the mixture will not be same in each well because of the unique characteristic of its formation, but the essential blend percentage can be written as 90% of water, 9.5% of propan, 0.5% of chemical additives. And the most common propan is natural sand that meets very specific physical, mechanical, and chemical requirements. These include size commonly varying from 100 mesh to as large as 10 per 20 mesh, pericity, mechanical crush strength, and very low solubility in acid. Synthetic propan are used for special applications such as deformation, and the more common composition are ceramic, bauxite, walnut hulls, or even plastic. The latter two are lightweight and used mostly with very low viscosity fluids.
Common additives used are viscosifier or tearing agent. It's for used to increase fluid viscosity to help transportability of the propan inside the fracture. Example, commonly polymer like gum, hydroxyethyl, cellulose, or HAC. The next is friction reducer, used to reduce the tubular friction and subsequently reduce the pressure needed to pump fluid into the wellbore. Example, additives such as polyacrylamide-based compound. The next additive is breakers, used to break the fluid and reduce its viscosity after the treatment so it can flow back and allows for clean up the propan pack. Example, oxidizer, acid, and etc. The next is clay stabilizer, used to prevent the water from interacting with reservoir mineralogy and eliminate damage of swelling clay that may exist in formation, such as potassium chloride, sodium chloride, and aluminium chloride, or etc. And the next additive is surfactant or mutual solvent, used to reduce surface tension of fracturing fluid to improve the fluid recovery and compatibility between the fracture fluid and formation matrix or formation fluid. The next is cross-linker, used to increase the molecular weight of the polymer by cross-linking the polymer backbone to a 3D structure and increase the elasticity and propan transport capability of the fluid. Example, boron, titanium, zirconium. All the compounds, water, propan, and additive are mixed together to form the frac fluid that must initiate and extend a cleavage or fracture of the reservoir producing minimum level of pressure. Suspend and transport particles such as graded sand deep into the fracture to hold it open up for drainage of hydrocarbon from the formation to the wellbore, not leak into the formation matrix, displacing or compressing the reservoir fluid, exhibit low pressure loss in the pipe due to friction. The velocity of the fluid in the fracture greatly determines how the propan settle in the fracture and it is carried away into the wellbore. Be compatible with the formation minerals and fluid, not cause precipitates, not damage the formation matrix permeability by establishing fluid block, particle transport, precipitation for plugging by transport of the fine particle, and be easy to remove from the fracture after test has been completed.